So what we see here is a clean damage of a tensile specimen undergoing ductile damage. And in order to generate this kind of result, of course, you need to understand all the steps required to do this, and also the meaning of the parameters in the sample, how significant they are, so that in the end you'll be able to set up a model similar to what I've just shown here, so that on your own simulation you'll be able to use it. If that's what you're interested in, then sit back and relax as we get started with this video. So my name is Dr. Michael Okere. I'm an associate professor within a UK university, and I'm the host of this YouTube channel where I try to help you create effective computational modeling solution. So the essence of the video today is to explore ductile damage of a cylindrical specimen. The sample that we're going to test is an ASTM E8 cylindrical sample, and this is sort of how it's going to look. It's a dogbone sample, and we are going to work with this sample. The dimensions of this sample are in millimeters. So if you're interested in how this sample can be created, this is a video that I've made that will show you in detail of how you can create this sample. If you are not interested in doing that and you just want to follow along with me, please look at the description section of this video where I've put a copy of this sample for you to download and use as you begin to explore what is going on here. So let's go into ABAQUS and get started with this. So when you get hold of the ABAQUS CAE file, which of course you can obtain from the description section of this video, so you will see that this is the way the specimen has been designed to be. So basically the gauge section here exists. So we're going to partition those two ends. So the option we're going to use is to go under here, and I'm going to select the option that says I want to partition using a point and a normal. So I select this point, and this is the normal direction to that point, so we've got a partition there. So the other point that I want to select is this point, and this is the normal direction. So we've got all those. So the next thing we now need to do is to partition them. So we're going to come here and use this option. So I'm going to partition based on, so basically I select everything, and the cells to partition is done, and then the datum plane I want to use is this, and then we'll create the partition. So that partition is created. So these are 3 different regions. And so the next thing is I will select this other end, click done. So that's my datum, and then I'll create partition. So this way we have different partitions structures for this material. So once we've got that, we can go back to the mesh module, and then at this stage you can see everything is now in yellow, so we can now use hexahedron. So if I select this option, and then so hexahedron, a sweep meshing algorithm, advancing front, so we can now go through. So if we now mesh this structure, so everything looks beautiful and fine. So the other thing that we just need to do while we are still at it is to make sure we assign the right mesh properties to this structure. So this is the assign element mesh type. So we select everything and click done. And so now it has to be an explicit, okay, because we're going to ultimately run an explicit simulation. So 3D stress element. So we'll now go through, so I can allow for a geometric order of linear. A radius integration is okay, there's no problem. What we really want to do is to scroll down here and get to the point where we have element deletion, because we know that we want to delete the elements that have failed. So element deletion has to be set to a yes. And what is the maximum degradation? So we need to specify a maximum degradation. So what this really means is the percentage of reduction in stiffness of that element that you want before you can make that element a candidate for deleting from the model. So in this case, I'll probably use 9.98. So that means 98% of the stiffness of that element. Using the damage variable, it will be degrading the stiffness up to the point where you're looking at 98% of that. Once that is done, then this element becomes a candidate that you can delete. So once we have all that, we click OK. So this way we specify the right element behavior. So the next thing we're going to do is to look at the materials. So if we then go back in here, so under materials, so we're going to create a steel material. So steel material, and the first parameter we need to get here is the density. You know that the density of steel is 7,800 kilograms per meter cubed, but because our dimensions are in millimeters, so what we're going to do is we need to convert it from meters to millimeters. And so kilogram per meter cubed, if we multiply by 1 meter cubed, same thing as 10 to the power 3 cubed times cubed of millimeters. And then with this we can cancel out the meters, leaving kilogram per millimeter cubed, but that means we then have to factor in this 10 to the power 9. So our density will have to be 7,800 times 10 to the power minus 9 kilogram per meter cubed. So here in ABAQUS, so what we'll put here, 7,800 e to the power minus 9 for density. which is the first term in this model. Now the next thing we need to think about is the elastic properties of this material. So if we click on the elastic properties, so let's look at the theory of what this says. For elastic properties for this, so what does that mean? So in the elastic region, we have the linear elastic region. So if you've got an experimental data that you want to model, so going to the linear elastic region, which is the proportional region between stress and strain, find the slope of that elastic region, and that will give you the modulus. So in this case, this stress and strain are in terms of true stress and true strain. So the slope of that initial linear elastic region will be 210 times 10 to the power 3 Newton per millimeter squared, and then V will be 0.33. So if we come into ABAQUS here, so this becomes 210 e to the power 3 and 0.33. So this way we specified our elastic properties. So if you like what you're seeing in this video, I just want to take a moment to like this video or to subscribe to the channel if you haven't already done. I really want you to continue to be informed of what is going on with this CM Videos channel, where I try to spread the message, spread the gospel of computational modeling, showing you effective ways of doing things and explaining what is really going on here. So if you have not subscribed, please do subscribe. And if there is a particular video you have in mind that you want me to make, please leave it for me a comment in the comment section. I do read all the comments and I try to respond and make videos to support students. If I can't, but where I can, I'd like to make videos to support you. So please take a moment and leave me a comment of what you think and ideas of videos you would like me to make. Thank you, and let's get back to the video. The next thing is the plastic properties for this material. So once you get to the end of the linear elastic limit, you get the yield stress, and then from there is this non-linear dependence of stress on strain, and this is where we get the plastic behavior. So the material begins to plastically deform. So we've got this section, so it starts from the yield stress and then it finishes at the ultimate tensile stress. Yes, so we need to specify this parameter for our model in order to capture the plastic behavior of the system. So that region under that graph is our plastic region. If we look more closely for this material that we are testing and put some numbers in that, so we get that same behavior, except that in this instance we are plotting that yield stress, or the stress from yield upwards up to ultimate tensile stress, against the plastic strain. Plastic strain is equal to the true strain in the material minus the yield stress divided by the Young's modulus of this material. So this will give you only the plastic strain, because you're going to use the plastic strain to quantify post-yield behavior of fracture damage. So we need to have a measure of this plastic strain, and with that we can have the numbers. So this is all of the number that we're going to use. So we're going to copy this number and put it into our model. So if we come into ABAQUS again, so mechanical plasticity data. So now we want yield stress and plastic strain. So if I paste that, so that gives me all the data, the yield stress and the plastic strain. It is in unit of Newton per millimeter squared. So the yield stress is 250, the ultimate tensile stress is 370, and the biggest plastic strain in the model is 0.28. So for the next stage, so what we see here is that the system will continue to go on forever and ever if there is no fracture on the system. Then we know that the material can't really exceed beyond the ultimate tensile strength, because that's the load bearing capacity of this material. But if you decide, look, I want to, right at this point where you get to ultimate tensile strength, if you release the load, you get an unloading behavior. And what will happen within the unloading behavior is that the material just follows this straight line until it comes to residual plastic strain, which is called the epsilon 0 PL. So it's a locked in plastic strain. What this means that because this material has gone to a plastic behavior, so if you imagine it's bent, so even when you take out the load, it's not able to return back, to snap back to the original state. If you are stretching it and it's got into plasticity, if you take out the load, it's not able to snap back to the original state. So this unloading profile is defined by this E value, and the strain at which that happens, initial plastic strain, the locked in plastic strain in the material. And so it takes the same slope as the straight line. Okay, so typically what you want to do is that you take the measurement of the slope and then get the extraction, extrapolate that line from that point according to that slope of that line, and that gives you the epsilon 0. Now we know that this material wouldn't necessarily do that. It will start failing, and because it's going to fail, a potential pathway of its failure will be this blue line, and then the ultimate point when it will fail will be the fracture strain. So the region around here is called the damage region. So for this case of the model that we are looking at, the original or the maximum plastic strain was 0.28. So that's what we saw earlier on. So that's 0.28. So this is the biggest plastic strain. So it's the end of our plastic region. But then we also have to note what the final plastic strain would be, the fracture plastic strain. And in this case, we are taking it as 0.35. So this normally will come from experiment or from a material data sheet where they give you an idea of what the fracture strain of this material would be. In this instance, it's 0.35. One feedback that you need to note is that your fracture strain should always be bigger than the maximum plastic strain. If it's too little, then you have a sort of a brittle behavior. If it is too large, then you have an unusually ductile deformation, which sort of will not make. So if we then go back into ABAQUS, we want to put that value of 0.35 because that's a critical parameter for us. So here in ABAQUS, how do we represent this onset of the fracture? So again, we go to damage of ductile materials and use ductile damage, and this becomes our 0.35. The next parameter here is the stress triaxiality parameter. So what does that mean? The stress triaxiality material, we're doing a simple tensile test. You've got the sample and you're pulling it apart. So what do? Now the stress triaxiality term, which is normally represented by this parameter, is the ratio of the hydrostatic mean stress, normally called a P, divided by the equivalent von Mises or deviatoric stress, normally represented as sigma equivalent. So this number is called the stress triaxiality term would be. So we want to find what it is in terms of a simple tensile test. A typical stress tensor of that would look like this. So all you would have here would be a sigma 11, which is the load of the stress in the 1 direction that you are testing, which is something we represent this way. And then all the other terms in this stress tensor will be 0 because there's no axial stress, there's no third axis stress, and there's no shear stress in a simple tensile test. Now, if we look a bit more, so this stress, hydrostatic or mean stress, is basically the trace of the stress tensor. In other words, we want to say the mean of the stresses in the diagonal direction. So sigma 1, sigma 2, sigma 3 divided by 3. So basically, this is what you have. And we know that in this instance, that these 2 and 3 stresses are 0. So ultimately, the P term, the hydrostatic mean stress for this simple tensile test will be 1/3 of a sigma 11. So that's number 1 of the term. So what about the equivalent for mean stress, which is the deviatoric stress in this material? So there's a longish expression that kind of helps us quantify this equivalent for mean stress. Von Mises is the stress that you normally see by default when you're running an ABAQUS simulation. So this is a mathematical definition of that von Mises stress. All the 2 and 3 stresses are all 0. All the shear stresses are all 0. So that means the only thing remaining will be this sigma 11 and sigma 11. So if we then simplify and evaluate that, you end up finding that the equivalent stress is simply the stress in 1 direction for this material. So we can then work out what the stress triaxiality would be, which we say is the ratio between P and sigma equivalent. So 1/3 and this, so leaving you 0.1/3, which means the stress triaxiality for a simple tensile test, as we are trying to do here, will give us 0.33. So we're going to then put that in ABAQUS, which is here, and we'll put 0.33. So the third one is the strain rate. So in terms of this strain rate, what we can say here is that for strain insensitive material, it makes sense to just make it a very small number. So we normally will put a 0 there. Now, where is strain rate sensitive? You rather will provide a table of strain rates and fracture strain and triaxiality. So you must have an understanding of the interaction of these properties, and it becomes a table. So in this case, we are trying to model a strain rate insensitive simulation. So we'll go here and put in a 0. There is a sub option here that we need to further, and that is our damage evolution. What goes into the damage evolution? So if you study the damage evolution, you can have a displacement damage evolution or an energy damage evolution. So you can specify the fracture energy in the system or the displacement at failure in the system. And how the damage will happen can either be by these 3 measures, which we'll speak about in a moment, and then we're going to use maximum degradation. So let's go back and study the theory behind this. What about the damage evolution? So in terms of damage evolution, so we get back to the state where failure has been initiated and has been detected. We now want to know, how do you go on this pathway where damage is evolving? So at the onset of damage, there's a damage variable that we define. That damage variable will normally have a value of 0. So this is initiation of damage. It will have a value of 0. So this is coincident with the point where the ultimate tensile strength of 370 exists. All right. So now, as the material keeps damaging, what you'll notice here is that there would be this movements of how the damage is evolving. We don't want the system to stay here, so we need to apply a damage variable to it so that it can start from here and get then adjusted from what it was virtually without damage to the actual value here. And so the effective stress on that material would be equal to 1 minus the damage variable. This damage variable takes a value between 0 and 1. If it is 0, it's onset of damage. At 1, is complete damage. So somewhere in here, this damage variable is a number, so it could be like 0.5. So 0.5, 1 minus 0.5 gives you 0.5 times the stress at that point. Initially, it pushes it down to this point. So we get this effective stress state that is acting in the model. And then the next thing is each of these lines will then be different lines. So for example, with the point of reference, so if you stop that damage, unload the system, hopefully it should return back to some residual plastic strain, which is epsilon 2 PL. So how do we get the slope of its return? Remember, when damage initiated and then we release it, the system just go to this point. Now, these ones will also have different slopes because we are also multiplying our Young's modulus for that material by this damage variable of 1 minus D2. So this is what within ABAQUS speak is called degradation. So you're degrading the modulus of this material during this unloading form in order to get to a point where you've got a locked in plastic strain. That's what the damage evolution would be when damage is completed. So D becomes equal to 1. So the effective stress at a fully damaged state would be 0. And so this is how we then have this variable D that sort of adjusts whatever the original virtual stress state would be into a realistic stress state, degrading the modulus of the material until ultimately you get comprehensive damage at the point where D is equal to 1. So that's really the damage evolution. But then there's something hidden within this which we are not sure of, and that's how is D able to accomplish this. And so how does damage evolve within the element that first meets this failure criteria? So there's a criteria that's running behind the ductile damage criteria. Once the element meets that criteria somewhere in the bulk of the material, what happens to it? So let's say that element look like this. So it's a single element and we just extract it from the bulk of the material. And when it meets the criteria that, okay, there's damage that is happening within it, and what will happen to it? So the damage variable D that we spoke about before is actually a function. It's dependent on a lot of parameters. The current plastic strain, which is the strain at this point, the reference plastic strain in the elastically unloaded state at the initial point, which is this, the fracture strain of the material, which is the point of total damage, and then the stress triaxiality term. So there are different equations that you can use to connect D to all these parameters. And the implication of that is that there has to be an evolution law, a damage evolution law that connects all those terms to D. And so the damage evolution law, or what ABAQUS call a softening law, could be linear law, tabular law, exponential law. So if we go back to ABAQUS, under the softening, so you have a linear law, exponential law, or the tabular law. So this is how the material is going to experience damage. So let's just have a quick look at this different law, and then we'll now apply it again to our model. In the first case, what you have a linear damage evolution law. So a mathematical expression for how D is depending on the other parameters we talked about will look like this. And so you have a linear dependence, which is what this line is. Now, what about the tabular damage evolution? The things that the damage evolution of a linear may not always capture what post-yield behavior that you get. Your softening law, it may be a bit complicated. It may not always proceed in this nicely linear form. And so we have a tabular damage evolution law. What I've done here is to generate these three possible cases for a brittle material, for a moderately ductile material, and a highly ductile material. So what would their damage evolution potentially would look like? So what you can then do in this instance is that instead of having just one straight line dependence between D and plastic displacement or plastic strain, you rather would have a tabulated reading where the system is going in this way. So normally this would be calibrated based on an actual experiment so that your model prediction will fit experiment. So if you get to a point where you're running a simulation, you find that your post-yield or damage evolution is not working well, then try and calibrate some sort of damage variable, providing a tabular data until you get a perfect fit within your material. The third of them all is an exponential damage evolution law. Again, for certain instances of simulation you're running, it would fit using an exponential case. The expression of how D is dependent on all the other parameters will also look like this. What is unique here is that we're introducing an alpha term. So if it is epsilon alpha is 0, then it becomes a simple linear evolution law. If it is alpha is other numbers non-zero, then you have different expressions. So you may have to play with these expressions in your modeling in order to get the perfect representation of what damage evolution or damage post-yield or post-damage expression you get in your model. So if we come back to this particular case that we're dealing with, so we are going to work with the linear law, and the only parameter we are required to specify here is our displacement at failure. This failed element, can we relate its fracture strain to the displacement at failure? Of course we can. For a linear case, we are assuming this relationship, but the displacement at failure will be expressible in this form mathematically. So basically, displacement divided by the original length equals strain, the fracture strains. But just that this length is called the characteristic length. Remember, we're dealing with an element, so we want what is the characteristic length of the element. Different elements will have different characteristic lengths in them, but for the case that we're dealing with, which is sort of equidal element, the characteristic length is actually the cube root of the volume of that element. So for this element with a length, width, and height, so the characteristic length with the cube root of that length, width, and height for this element. And what you need to then do is to find the potential element within the microstructure to sort of give you an idea of how this length, width, and height of the element, and then you can use that. So we want our displacement at failure. So I'm going to activate the mesh module. So what I've done here is I've come to the gauge section. I expect that within the gauge section, the element is going to experience failure. So I want to see what is the volume of one of the elements. So if I zoom into one of these elements here, let's say I pick up that one, and then I need to go to the top here and say replace the selected. So I'll click on that, then every other thing around it will go, leaving just that element in question. So clearly, because it's a circular shaped structure, so these dimensions are okay, but then these ones are is going towards the center line and it's looking like that. But that doesn't matter, because in the end we just want to have a reference of what potentially our displacement at failure would be for the element. So we carry this element, and then we need to measure the length, the width, and the height. So what do we need to do? So you click on that on good distance. So I'll say let's look at the length, so from here to there. So what we have here as our distance is 1.25, so I'll copy 1.25, and then I've got this Excel sheet which is again available for you to use. So I'm going to paste that length there. So I'm going to look for the width. So what would the width be? So again, the distance from here to there, so that gives me the width again, 1.25, and then we'll paste it there. So the height will be from here, let's say, to that point. So we get the height again, 1.225, so slightly different number. So we expect that this material will have different values. Okay, so these are the length, the width, and the height. Then the volume of that element will be multiplication of all three, so that gives us the volume. And then the next thing is the characteristic length. Remember, the characteristic length is the cube root. So what we have here as our displacement at failure will be the characteristic length times the fracture strain of the material. So these are the two terms that we need, and we get 0.44 approximately as our displacement at failure. So if we then go back to ABAQUS, we can now ask it to replace all the elements, so everything comes back, and then we can go to our materials and then try and specify what our damage evolution would be. So we didn't really specify what the damage evolution would be. We said it's 0, so we now need to put 4 around there. So that becomes the displacement at failure for this material. So we can then create a section. So the steel section is fine. So we can now create an instance for our assembly. Now, still within this, we can create some sets. So I could call this my bottom grip. Bottom grip will probably be in this region. And then we can go to the top and say my top grip. My top grip would be in that point. So that's fine. So there are a few other things that we want to apply loading on the system. So we need to then introduce sort of a point here. So if I click on this, so I want a projection from there. So select a point. So somewhere here is where I want my point. And how much am I projecting? I'm going in the x-axis. So if we do maybe like 10. Okay, so we've got a reference point there. So what we can then do is, okay, tools reference. So I'm going to select the point that we've created. So that's our reference point, and we need to create a set of that reference point. So I'm going to call it reference point set. So our step, so this will be our loading step, and we are going to use a dynamic explicit to set up the model, and we leave all the cases, everything here by default. You may have to do a mass scaling if you want to quicken the speed of the test, but we're going to leave everything as basic as it is. So in terms of our field outputs, so we must make sure that within the field output, as we are setting it up, we have to introduce a state variable. So under the state here, we look for status, because what the status variable does is, this is how the simulation checks and say, okay, does this element meet this criteria where our d value is approaching value of 1, is getting to at least 0.95, the maximum degradation of 1. And if it gets to that value, it says this element has met the criteria, delete it. So it's a status parameter that allows you to be able to do that. If you don't have it in your model, element deletion would not happen. So we can then look at some constraint equations. So we're going to say, okay, I'm going to put some constraint equation, and I'm going to use kinematic coupling. So I'm going to couple two parts. So I'm going to couple the reference point set to a nodal region, which is the top grip. We accept everything that is there. So basically whatever is applied here will be transferred to that whole region. And then we can then apply a boundary condition. So I'm going to say fixed base, because we need to fix the back using displacement condition. So the bottom grip is fixed, and we are fixing it in every possible direction, because that's how it will appear in the grip. It's going to be fixed in the grip. So I'm going to apply my displacement. So displacement load tension, and it will be a loading step, and we are going to apply it on that reference point, and we will only, so if we activate everything, so this is where we want this value to be some number. So if we make 20, now we need to also create an amplitude. So if we click here, we want a tabular amplitude, so we're going to call it load amplitude. So I want a tabular amplitude. So this is the table that we're going to use. So I'm just going to copy that value, and then I'll paste it in here. So we've got our table and amplitude created. We need to just accept it here. I mean, we could also ask it to give us a history variable for the sake of what we want. So I'm going to call it my reference point history output. So it's going to be on the set of that reference point, and we want RF1 U1. So the reaction force in one direction, displacement in one direction. So, and that's what we have. So everything is all done, and then we can then create the job. So this is sort of what the simulation result will look like, and then ask it, so it begins to deform, accumulates, and then we get a plastic deformation right in the gauge section as anticipated. So we get a fracture. So we get, obviously there are tentacles of the samples that are not allowing it to fail, just as you would get in real experiments. You know, we've got tendrils or tentacles as the sample is trying to deform. So there's a clean breakage of the damage, and it's breaking right in the gauge section as expected. And so everything around this setup is perfect, because we have set it up properly in the way it should be. And so this is an excellent set of results that we're happy with, and then it captures everything that we need. So if we look at the plastic strain, so that's what you see here. So right in the gauge section here, the plastic strain builds up, and then it fails plastically, and you get a plastic deformation in this material, and it looks really good. And the reason why this is so is because we have done it properly by calibrating it properly with all the parameters required. And the final thing really is to then look at what the stress strain data, or what the result would be. So if we go here and say, okay, fine, we're looking for the history output. So we continue on the history output. So we have asked it to give us the reaction force and the displacement. So if we plot that, then it gives us a nice picture of the elastic region, the plastic behavior, and then the fracture behavior as expected. And then gradually the same is just tethering because it has already failed. So what we can then go and look at this data here is to two plots. So we know that, so the temporary data number 1 there would be our reaction force, and then the temporary data 2, we'll name it, and that will be our U1 data. So the next thing we need to do is basically to operate on that. So what do we need to operate on that? Operate on this data. So basically we use the combine option. So here is the combine option. What do we have here as our strain? Our strain will be this term divided by the gauge section. So we know that our gauge section is 50, and then what we have here will be the reaction force divided by the area of that will be 3.14 times the radius of that gauge section, which we know would be 10 times 10. So that's what we'll have in terms of our stress and strain data. We'll plot that and we'll plot this expression. But we need to change these references to stress and strain, so force and displacement. So with this way we change it so we get our stress and strain data. So this is how you can undertake a tensile deformation for a material that's undergoing ductile damage. It's an extensive video showing you all the required steps. If you want to see how this sample was created, like I mentioned earlier on, then this is the video that can help you. If you have not subscribed to this channel, please subscribe so when content like this are made, you'll be the first to see it. Thank you, and I'll see you in the next video. Bye bye.